We present our work, Deep Reinforcement Learning with Dynamic Graphs, for Adaptive Informative Path Planning. Efficient data collection is a key requirement in many monitoring tasks, such as environmental mapping, precision agriculture, and exploration. However, complex 3D environments have previously unknown obstacles and occlusions, making the informative path planning problem challenging to solve. For scenarios such as fruit monitoring, the fruits might also be partially occluded by the tree leaves. In our problem setup, we consider an unmanned aerial vehicle equipped with a unidirectional sensor to detect targets of interest in an initially unknown 3D environment, such as fruits in orchard, as efficiently as possible. A key aspect of our path planning approach is a dynamically constructed graph that restricts planning to actions local to the robot, allowing us to quickly react to newly discovered obstacles and targets of interest. In our approach, the robot maintains a Gaussian process and occupancy map to represent the environment. At each time step, our approach samples collision-free waypoints in the robot's local environment. These waypoints, with considered yaw directions, generate action nodes. Each action node is associated with utility and uncertainty value, regressed from the Gaussian process, to generate the dynamic graph. Our actor-critic network uses the dynamic graph to output the v-value of the robot state and choose the next action to execute, which generates a reward and observations from the environment. The experience buffer stores the variables utilized to train the actor-critic network. The blue arrows indicate robot control loop and the green arrows are variables stored in experience buffer. To capture the adaptive informative planning objective, we propose a new reward function that encourages the robot to both explore unknown regions and exploit detected targets. Our approach outperforms state-of-the-art learning and non-learning baselines by a significant margin in terms of detected fruits. This can be attributed to the new reward function that balances between exploring the environment and exploiting collected information. We demonstrate the applicability of our approach on UAV in an orchard environment simulator created with Unreal Engine and AirSim. We assume perfect localization and use ground truth apple object detection. Here, the pink line is the trace line for path followed by the robot. Our apple orchard environment has 9 trees arranged in a 3x3 array and a total of 225 red apples at random locations on the trees. We record the coordinates of detected fruits to ensure that the same fruit is not counted multiple times.